So far on the Future of Architecture, Programming for Architects, Introduction to Computational Design, we've discussed a couple of things. We've looked at your course overview, and we did crafting your career, the trends and movements, the critical evaluation, your choice of path, and we also had to look at your path that you created with its timeline. And hopefully you have a 6-month to 1-year timeline that you're going to follow quite studiously. You had a task to do there, which was tying your shoelace, and we're going to try now to move on from that idea into the programming concepts, which you did discuss very quickly yesterday. In fact, you actually managed to program and do some programming, some sort of algorithmic script that you've written. Here, as you can see on the screen, we have concepts. And these are some of the concepts we started with yesterday. We spoke about data transfer, storage, and paths. But we didn't say in those exact words. We're going to get into some more of those words today. But what we didn't talk about is discrete mathematics. And what we did talk about is printing, strings, data types. And what we didn't was Boolean now. For all the things we didn't, we'll talk about now. And for all the things that we did talk about, we'll review it again. Then we're going to end off with a task. But let's do a little twist on this. Let's start the task now and see if the lecture helps at all. All right, so what we have here, now that we've discussed it a little bit more and thought about what your inputs are, and you kind of tested out the program for yourself and it's working or it's not working, let's try and see if we can understand what is actually going on. I'm going to take you through a very summarized version of programming. And this is by no means a comprehensive understanding, but it does sort of wash over the entire thing you call programming. And I'm not going to try to attempt to define programming. It's quite broad and it would take a long time. But what I'm going to do is tell you what is programming about, so that we can move around the idea of programming and try to define it from the outside going in and make a clearer picture. So programming is about a number of things. And one of the things that it's about is data. Now, data can be seen as information and what you might call bits and bobs. Probably bits is a nice word to use, because it's little bits of information, small little bits and bytes, words we're going to probably use a lot in the next few slides to come. Data looks like this, little bits of stuff falling around, information scattered, sometimes meaningful, sometimes meaningless, but we call information and data more or less the same thing. It's almost as though it's unprocessed knowledge. And that's the thing I want you to write down and keep it. You can keep it with you and keep it close to you so that you know that this unprocessed bits of information is like knowledge that's untapped or not yet tapped. And we need to tap into it. That's why we need to do something with it. So this is what it is. It's all around in the world around. The important part about data, and the thing that makes it so cool, is that it can be stored. And this takes you back to many times. I want you to just try and expand your thinking a bit. Think back to when we had, say, the first alphanumeric text, the first alphabets. Now, alphabets, according to Mario Karpo, in the book, The Second Digital Turn, in the second digital turn, what Mario Karpo does is he talks about how society has progressed and how we have invented technologies to help us do it. Alphabets, as the common words there. The alphabets are compressions of information that we have, translated into a portable format so that it can be stored and transferred and retrieved later. So as I'm speaking to you, what you would do if you're probably listening and taking notes is you are hearing what I'm saying, taking that information, processing it into some sort of graphical, user-friendly format so that you can see what it is. And we all have to understand what this graphical layout is in this format with these lines and scratches and dots and spaces in between. We call those things syntax. The dots, the spaces, the formation of the letters, the parentheses, the commas, the colons. We call those things the syntax. Because the syntax is in a particular format, you have A, B, C, D, or you have a letter or a word, and you're writing whatever I'm saying, you can then understand what it is that I'm telling you without me being there, because you heard me and you wrote it down. And then you can read, you can retrieve that information which you stored on the page again later. What you did is you compress the sound that you heard into something a little bit more portable, and that can be a little bit more durable. Because you heard me speaking, you'll forget it. So you need to record it or store it. So you wrote down what I said on the page in a syntax, a format, a layout, graphics that you can understand, someone else can understand, we can all understand, so we can retrieve it later. That's a form of technology. And that in itself is you computing information. You are behaving like a computer. It's not very different to what a computer does. Now we store information, we transfer information, and we retrieve it. Whenever there is a change in the way we do this, a revolution occurs. So you could say one of the first revolutions that has occurred in the way we store, transfer, and retrieve data is language itself. Me talking and you understanding. Then us recording that on paper so it lasts longer than in our minds. It's being stored for a longer time. It's like the memory has been stored for longer. How's those words? Eh? You come across them soon. So it's being stored for a large period of time or a long period of time. And then it's being retrieved again. And so we have you talking and now we can hear and you can communicate. I can tell you if there's danger, if there's a bird coming to attack you, or if there's an elephant that we need to, I don't know, maybe ride or something, or maybe there's a storm coming. I can tell it to you, you can hear and understand. But what if I wanted to record it for later? So then we develop a written language, as you might know from the history of architecture. And then we have new ways of storing that stuff. We have things like a codex. We take all this paper or this format that we've written it on, the substrate we've written it on, collected it, put it together, and then we easily reference it whenever we need to again. And we have it not in long rows of parchment, because then we have to look down the entire list for something we want. And we have to go in a sequential format, walk maybe a kilometer before we get the information we need. If we could just fold it up and compress that into a format like a codex, we can now very easily just scan through a few pages and get to where we want to be very quickly. But now what if you could take that information and store it digitally, okay? Or on some sort of electronic device and then retrieve it? And because we're working with electrons, because electricity, it moves and can be commanded, now the information we have almost dances, moves around. So that information, that data, it becomes meaningful to us, and we'll call that meaning knowledge. Okay. Here's an image that you can see on your screen. What we did is, from the last image, we have data. And now you can see that data is being contained. It's being stored. And after it's being stored on the left, you can see it moving towards the right-hand side. Now it's being transferred. Right? These little bits and bobs. These bits, a bit, like a 1 or a 0. Oh my gosh, that looks like a 1 or a 0. Coincidence? I think not. So anyway, we have this stored in these containers, which are then being transferred. And so, well, it's stored, transferred, and retrieved, going back out. So we have information, we're storing it somewhere. It could be in a book. It could be with electrons or electricity. Electrons, electricity. Where are we getting at for that? Okay, so electrons, electricity. And you could store it, I don't know, maybe on your phone. Maybe now you can store things instead of under your bed in a bank account electronically. Electrons, electricity gave us the ability to store information in a different way. We can store it, and that's what the little boxes are for. The arrows are for transferring, and then going back out is retrieving it. Store, transfer, retrieve. Following so far? I hope so. Let's have a quick discussion to see what this means. So now let's hope you understood from the first principle perspective, more or less how we've derived this idea of storing, transferring information. What comes after this? Programming is about those things that we just mentioned, but it's also about the truth. Now, the truth is something mankind has been searching for a really long time. You want to find out the truth about many things. You want to find out the truth about the reason we're here. You want to find out the truth about, say, your work that you're doing. Is it really helpful, beneficial to the world you're living in? You want to find the truth behind lies. Maybe you think politicians are liars. Maybe the truth helps you get to the destination you're getting at. Whatever it is, when you're driving, you can maybe put in the wrong GPS location. But in all of these things that I just mentioned, there's many ways to get to the places you want. There's many ways to figure out what the meaning of life is. There's many ways for you to determine if someone is lying to you or not. And there's many ways for you to get to the destination you want. And all of them can be truthful ways or ways to get there. But are they all correct? Are they all the one that you want to go to? Keep that in your mind. So as you can see here, those little arrows we had just now are now colored in red. And they're colored in red because this is the only way that this information can come in and go out. Why? Because as you can see, the walls of these containers are broken in certain places. And as you would know in our architectural languages, wherever there's a break in a wall, it means you can exit. You either put a door there, or it's just an opening, or there's a window. That's more or less what you have. And so the arrows can move between that. the bits and bobs and bytes, they can all move between these things. Right? Truthfully, it can. That's why it's in red, because that's the way it can move, because there's an opening. But the absolute truth is a little bit different, but kind of like the same. So the absolute truth looks like this. It's all the pathways that exist, and they are all different, but they're moving in the same direction. Something that's not the absolute truth is going to be moving in the wrong direction. And what you can see here is that it's barging up against walls. It's almost getting blocked. There's an obstacle and you can't get around. So this is when we're looking at something that's not the truth, not the absolute truth. And so the absolute truth is more the idea of the direction you are going. So as you can see, the absolute truth is it must go in this direction. I'm not exactly sure the paths to take it there, but I know there are paths, but the direction is the absolute. And that's what programming is about as well. Because once you have the truth, there's only one direction you need to move in to get it, but there's lots of ways to get it. So now that we spoke about these pathways toward the truth, you can imagine it's something like this. Here's all of these weird pathways that we are walking around, and you can go into many different directions and different ways to try and obtain the path to salvation and the truth and the way finding yourself out. But if you don't have the truth, you can't get anywhere. Anything built on lies, as you see here, even if you think you are moving in a particular direction, you're going to hit a dead end. The programming is about the truth because we are never trying to hit a dead end. All right, so pathways toward the truth, we have it here, and we talk about pathways, and we just spoke about electricity and neurons and neutrons and all that stuff just now. Why? Let's take a step back quickly. Let me ask a couple questions to those who are here. So now that we all have mistaken the word discrete for discrete, as in being secretive, D-I-S-C-R-E-T-T, it looks like the word secret there. And maybe this is the secret mathematics you never knew about. That's why it sucks. Because this secret mathematics, this discrete mathematics, this word actually means finite. To have something discrete means finite. It means it's either this or that. There's a limitation to it. So in discrete mathematics, because there's a limitation to it, because it's yes or no, true or false, if this, then that, you can see how this would lead into decision making. And you can see how this decision making is quite similarly related to pathways. And pathways to what? If you can see the screen, you can see we have our little bits and bobs we had just now. Here's bits and bobs and bytes. Bits and bobs are here. And what we can say is we have one bit of information and you have several bytes of information. So when there's lots of information together, we call it bytes, okay? Or a byte. Okay? 8 bits, 1 byte. 8 of 0 bits together, the things that are there, 1 byte. But now when you have a look at this and you see this 1 and a 0, or this bits and bobs together, coming together to make a sign you're familiar with, you start to notice these things appearing around you. If you look on your laptop now, or your computer, or the light switch in your room, wherever the case is, if you have a look at it, you'll see there's a 1 and a 0. That 1 and a 0 stands for on and off. That's really what it is. And that idea comes from discrete mathematics. On or off, yes or no, this or that, if, else, if, then, whatever the case is. It's binary. Hey, don't play games here. Binary. Hey, bi as in 2, nary like numbers, binary, 2 numbers or 2 types. I don't think nary is actually the suffix for number, but I'm trying to give you an understanding here. Binary, 2 types of things together. So we're saying the 1 plus a 0 gives you the on and off switch. Hey? And so really what we're looking at here, if you have to think about it, we're talking about paths and pathways. If you have to think about a circuit is a path towards light or electricity or towards something, but it's the electrons moving through the paths to get to something. And so when there's a break in it, you put a 0, a break in the circuit, or we'd have lines drawn, put a circle in the center. And when there's no break in it, the line itself will just continue. And so really what we're looking at here when we look at 1s and 0s is we're just looking at open or closed circuits, on or off. And when you have on or off, you are sending electrical impulses to a machine, to a computer, to a switch, and you just say on or off. And really what's happening here is you are setting up a series of pathways on and off, because if this one goes off, then the electron will move another direction as moving. This path goes off, move into another direction, and this one goes off, so move into another direction. All of these things is on and off. You're actually guiding the electrons to the place, to the truth, to the one direction it needs to move into. If this, then that. We call this Boolean. It's actually named after guys. Some people say Boolean, some people say Boolean. I'm going to say Boolean for now. What I just mentioned to you, if this but that, true, false, then yes, no. One or the other. That's the only two options we have. This binary logic, this binary type of thinking. That helps you with decision making. And in fact, it should be one of the key mathematics discourses taught, this logic, because this is the logic that's behind computer science, from discrete mathematics to computer science, which allows you to do programming. Programming in this new world we live in allows you to do this. Now we have calculus and we had algebra, and we had all of those things which have been very useful, and they still are useful. However, it shouldn't be the only thing that we taught, because those types of mathematics helped us a lot in the Industrial Revolution time to help us program machinery, or learn the habits of machinery, or learn the celestial motion of bodies in space and how to make machines move. It was very helpful, vectors and all of those things joined together. But now to automate it, we need this logic, the digital logic, how to program electrons, these small little baby things inside what we see every day, even within yourself. If we can program them, take them to a path, we can automate objects, and those objects can come to life, like this computer you're seeing on your screen now. Lights, that's all it is. If this, then that, on or off, lights. All you're looking at on your screen is a complex series of networks of pathways allowing lights to be displayed. And so what you're looking at here is a decision tree. A decision tree making decisions. If it's this, then it's that. And if it's that, then it's these two things or those two things. These flows and these diagrams that you're looking at is really all computer programming is about. It's about taking data through a series of if this, then that, so that it can get to the output it needs to get. And we'll call the series, these pathways, a logic and a structure. It must follow this, then that. And the way I like to think programming, or the way I like to think about programming is about logic and structure. Logic doesn't mean it makes sense. Logic means there's a path that needs to be taken. Whether that's sensible to you or not, doesn't really matter, that's inconsequential. But does it get to the end? Yes. And often the case is, getting to the end seems to make sense to you. So it's not too much about the how, although that is important. What's more significant is the at the end outcome. Okay? It's about the end. And so this logic and structure, the way you can think about it is narratives. Okay? When someone says you're not logical, they just mean they don't understand what you are doing. Doesn't mean what you're saying is not the truth. You have a different way of looking at the truth. You have facts that are organized in a way that makes sense to you. That's a logic. Perhaps somebody else's logic isn't that way. But if your logic doesn't get to the truth, that's perhaps what people are saying. People are saying you're not logical, they mean the way you are going on about things is not getting you to the truth, to the end ultimate outcome. And how do you do that? You set up a series of steps and structures. And so logic talks a lot about this idea of sequence. Logic and structure inherently are about sequence. You must do this first, then that. And that's what programming is about. Here, what you can see is a simple tree, decision-making trees. If this, then that, go this way. If you say yes to this, then do that. And you say no to this, maybe then. Here's all the pathways. It gets so complex that we can create lots and lots of sophisticated, or several kinds of devices. You can create machinery, you can create cars, you can create the computer, you can create the laptop. You can do so much by being able to control the flow and network of electrons that we have the devices that we use today. One of the things programming is about is also manipulating data. So let's take a small pause here to see if we can maybe reflect on the ideas we just spoke of. Okay, so if you were lost, and maybe you took some time to recap it, let's go through this again very, very quickly. Go through all of this from the beginning. I said in the beginning, I'm not going to try to define programming, but I want to say what I think it's about. And I said that I think programming is about data. It's about this information that doesn't make any sense to us. We've got to do something to it. We've got to process it so that it becomes meaningful, so it becomes knowledge. And so this data or information is just scattered and random. And what we want to do is we want to store and collect it and then transfer and retrieve it so that we could maybe use it. And that's what makes it meaningful to us, because we can store it and transfer it and retrieve it and then use it when we need to. And so we have these bits and bobs and bytes, all these little things around, and we're trying to store it, and we can store it. There's these containers for storing. We can transfer it, and then we can retrieve it when we want to. And after we've done that, I said programming is also about the truth. The truth are these particular directions in which this information flows. It can only move in one direction or in a particular type of overarching direction. But there's many ways to get towards that direction, many paths to take. However, this idea of absolute truth is the direction. That many paths lead in a particular direction, but not all paths go to the correct direction, the one that's the absolute truth. And as you can see here, there's some directions that are bumping up against the wall. It's not going to get you to your output what you want. Now, these pathways to the truth, as you can see, there's several of them here. This idea of following pathways comes back to decision making. What are the decisions or the paths that you will take to get to where you need to be? And this thinking comes from discrete mathematics. In fact, it's a very old form of mathematics. And this form of mathematics is actually very good for decision making. It's called discrete mathematics. And this discrete mathematics is what governs the way electrons flow in a circuit. And we described that the on and off button is really just about on and off switches that occur in your appliances or in your devices or whatever the case is. We said, okay, this on and off, true or false, if this, then that, allows you to create trees or decision trees showing the pathways. You can see it looks like a tree, so it's like a complex structure being formed. And the structure being formed, you call it logic. The path that you take to get there, you'll call it logic. And the structure in itself, the best way I can refer to it as, we say it's a narrative, following a couple of steps to get to a particular outcome. We have a simple, medium, and complex tree. But now, the last thing that we're going to say it's about, the last thing that programming is about, or at least for me, I think programming is about now manipulating that data. What are we doing? So we are making the data move, but we want to do a bit more than just make it move in and out or back and forth, to and from. In fact, this is probably 5 of the core functions that we can have a look at that we've been discussing in our course thus far. And it's summarized into a diagrammatic overview. You've come across some of these in Word and haven't really dealt with it yet, but I'm taking you through some of the basic core ideas of what we're doing to data. We are manipulating it. On the left-hand side, you can see we are inputting. And whenever we input data, the arrow showing the input of the data into a container, which we call variables. So we are inputting data. We are taking data, manipulating it so that it can be stored in a container. What we then do is, after it's being stored, we need to give it a place to go. So you can see the second image there is showing the logic pathways. Where is it going? Like in a circuit, where is this data going? Where is electron? You can look at the data and electrons as the same thing. For now, let's keep it that way. The data and electrons, where is it going? What is the logic pathway? After that, where you can see the third thing is the operations and the processes. So it's going to go somewhere, it's going to stop somewhere, maybe it'll get processed or changed or compiled. Compiled is a word that we're going to use when we say that electrons go into a device that's going to magically turn it into something that is helping the machinery, the utilities, your devices to understand it. It's called a compiler. So it's going into something, being compiled, and we're not going to talk about the complexities of the compiler, just accept for now, that's what a compiler does, so that we can get through the content in a useful, meaningful way for you to use it, a helpful way. It's going to go in, get compiled into the things it needs to be for the computer to understand it. And then the computer will take this and show it to you in a way that's meaningful to you, in graphics or lights or layouts or whatever the case is. This is a process. And so you can add things together, you can subtract things, you can divide things, you can do all of this stuff. But all it's doing is that this computer is looking where information is stored, recalling that information, spitting it out. Okay? It's getting processed somewhere in between. Something's happening to it, but that's all it's doing. Getting stored somewhere, being retrieved, albeit in a different format. And then what we have, now that we've had it stored and we have parts to it, and the parts sometimes process it, you can add it, subtract it, do things to it, magical, wonderful things. We can now go back, we can loop this cycle again, and we can look at each of those steps that we've just spoken about. You can go to each of those steps in a list, and you can recall it, or change it around, or mix up the order in which these things happen. That's these loops, they are cyclical. They allow you to review what has occurred. It's cyclical or cyclical, it circles, it's repetitive. And we call these loops. And you have a while loop, a for loop, several types of loops that you have. But this loop allows you to do these processes over and over again. Finally, we have the list, and the list can store things in a particular sequence or order, and you can extract from it in a particular order that you want. So maybe you stored something from A to Z, or 1 to 10. You can store it in that order, and you can go and look, okay, in position number 5, what is there? Oh, A, B, C, D, E. Oh, E, the letter E is in position number 5. And go into your storage container, pick up number 5, and give it back to wherever you want it. Now, these are the ways that we can manipulate data. These are diagrammatic overviews of the way we can manipulate data. And that's really all programming is. It's us taking into account small bits and bobs, these flashes of light, if you can call it that, if you will, flashes of light that we can see as on, which is a 1, or 0, which is an off, which so happens to coincide with the way we draw a circuit as well, as you saw here, on or off. We just take this information and we've made it really, really complex. We've added onto it, built it, made a series of circuits to show lights in different places. The keyboard lights up. The light you're seeing on the screen now is me put into a certain system of coordinates so you can see my face and my hands moving in a particular way. That same information is now being converted into airwaves, microwaves, waves, because light can be in a form of waves and sound as well, waves that are being transmitted over the air into the towers, coming back to particular devices, being reorganized and making light flash in a particular way so that you can see me. The wonders of the internet. But that's all that's really happening. People have figured this out over years, and we've shared this information so that you can get this knowledge that I'm sharing wherever you are, at whatever time space it is, whether you're in the same place as me or not. You've recorded a period in time, we've stored the information, we've transferred it, because you may be sending this via Google or WhatsApp or whatever the case is, and then we transferred it. Okay? We transferred it from one place to another. Store, transfer, retrieve. And you can put this on pause, go eat something, come back because you may be bored of me, and then listen to what I have to say. That's the magic here. Beautiful, isn't it?